we were just doing a linear program and we ended up with an objective function that said $10 per chair times the number of chairs plus $16 per table times the number of tables. And that kind of multiplying and adding is related to a bunch of different interesting things in math. So you might remember it as doing a linear combination from an intro linear algebra class. In this case, it's a linear combination of scalars rather than like scalar times vector plus scalar times vector. We'll be doing stuff like that too, but we're going to just keep it simple for now. You might also think of it as a dot product of the vector 1016 with the vector c comma t, which you might see in a variety of classes. The dot product of two vectors is the sum of their multiply their first components, multiply the second components, multiply the third components, etc., and then add that all up. You might also remember a formula that says that the dot product of a vector, remember the dot product of two vectors is a scalar. You can also express that as the length of one vector times the length of the other vector times the cosine of the angle between them, and we'll make a link with that in just a sec. Maybe you can also see how this is related to the law of cosines. You might remember from trig class. It's okay if you don't, but it's a nice link between interesting things. This idea of multiply things in pairs and then add them all up also happens in probability class, where we're talking about the expected value of a discrete distribution. We even do this for continuous distributions. We multiply things that are like probabilities, probability densities, by x values and then add those all up using an integral. And even when we're taking the plain old mean of data, you could write it as 1 over n times the sum of the values, but you could also see it as each individual value times a weight of 1 over n, kind of like the probability of seeing this value in the data set we have is 1 over n, because it's one of the n values in the data set. We can also look at formulas from a stats class, like the variance of a data set. I'm ignoring the whole divide by n minus 1 thing here, that's not important. But can you see how I'm multiplying some values, the squared deviations, by some weights and then adding it all up? We can also think of that as, instead of squaring, you could think of it as a sum product of three things. This thing times this thing times this thing, and then add it all up. The function we're going to be using in Excel can actually do an expression like that. And then here's where life gets even more interesting. If I don't want to just take the variance of a single data set, but I want to say how are two data sets that are paired related to each other, I can take the covariance, where I just replace this x and this x bar with y and y bar. So that's the definition of covariance. And notice that that's basically doing a correlation, right? Or that's basically doing a dot product. So somehow correlation is the cosine of the angle between the two data vectors in statistics, which is pretty interesting. Which means that covariance is part of the law of cosines of statistics. So I like the law of cosines of statistics. It's a little bit more complicated than the Pythagorean theorem of statistics, but it's even more useful. So I think I've convinced you that this idea of multiply the first two, multiply the second two, multiply the third two, add them all up is a big idea that happens in a lot of math. And it's such a big idea that Excel has a function to do it called SUMPRODUCT. So you can see how we're taking products and then summing them up. So here's how to use them, and we'll be using SUMPRODUCT over and over again. So I'll just start typing it here. You say SUMPRODUCT of this vector, like we said 10 comma 16, with this other vector. Maybe I'm making 3 chairs and 1 table, for example, and hit enter, and it will do 10 times 3 plus 16 times 1, and we get 46. Let me show that in with a vectors of length 3. So the big question here, so I'm going to say SUMPRODUCT. Maybe I have tables, chairs, and footstools or something. Should I highlight the first things I want to multiply and the second things I want to multiply and the third things I want to multiply, like this? So those, comma those, comma those. Well, if I do that, I get a number, but I get a number that's much bigger than what I would actually get if I do 10 times 3 plus 16 times 1 plus 7 times 2. So it's really sneaky or dangerous. It doesn't throw an error. It gives you a number, but it's the wrong number. So what I need to do instead is tell it which vectors I want to take the sum product of, not the individual pairs, but I want to take the sum product of that vector with that vector. Notice that, let's say I had like 100 components in the first vector and 100 components in the second vector. I can take their sum product by just highlighting one range, pressing the comma key, and highlighting the other range. So that's just highlighting two ranges. If sum product was engineered so I had to highlight each pair, I would have to highlight 100 pairs, and that wouldn't save me very much time at all. So sum product of 60 makes a lot more sense. 10 times 3 is 30, plus 16 plus 14 gives you 60. So I could, if I really wanted to, do this times that plus this times that plus this times that. But that's a lot of pointing and clicking, and you can see how you might accidentally make a mistake there. If I had 100 things in each vector, that would take a long time. So sum product is definitely the way to go on that. Like, you might have thought that I was your new best friend, but no, sum product is your new best friend.